Okay, hello everyone. Now we are starting with the tutorial. So this time the assignment has two portions. One consists of descriptive questions and the other is a coding part. So first we'll start with the coding part. So this time we were a bit late to release the assignment, but I hope you got time to just look at the assignment. So you can start with your doubts. If you have any doubts, you can start with it. So did everyone go through the assignment, at least the coding part?
So maybe you can describe each question, go from top to down, bottom, and let them ask questions. Yeah, sorry, we apologize. This time we were trying to uh,
This is
decide between written assignment versus a programming assignment. Then we decided let's do both.
okay. So yeah, this assignment was uploaded a bit late, but it is there on the course website. You can go there. It is there on the Shala website. Maybe you can just skim through and ask if you have any doubts. So this assignment is actually based on one. This it consists of two questions. One is based on finding log likelihoods, and the other is based on the t test that you have learned yesterday. Okay, so we have some questions. How to visualize a exponential distribution with various values of lambda? You can just plot, no? So there is a function in Cbon. It is sns.distplot. So it takes the values and then it plots a histogram sort of type of thing. So you can use samples and then you can provide some lambda and then you can plot it. So how to verify it visually? Okay. So in exponential distribution, you all know that mean is same as lambda, right? So you can just plot its distribution and then you can check it. So the mean is 1 by lambda. So yeah, so 1 by lambda. So by that, by plotting the data points, you can check it. So wait, I'll just show you. So as you can see, the mean is sort of closer to 0.5 as compared to 1. Okay, so by that you can tell that the lambda is equal to 2 is the better choice for this sample. We didn't upload a collab this time. We uploaded a link to the GitHub repository. You can it's there on the course website. If you click that, then you will get access to this notebook.
So Ipsit, are you taking questions from the chat? So there is one question. Uh, how to visualize exponential distributions with various values of lambda? So I think that you have answered, right? Or go ahead. I guess that should be straightforward. I meant how to compare actual distribution. I guess you just answered that one also. So exponential distribution, as Ipsit mentioned, has only one parameter, and that is directly related to the mean. It's the inverse of the mean. So if you estimate the mean of
I will
the
be start taking likelihood
samples.
1 and 2. Okay. So see, how do we find likelihood of a sample of random variables? We assume that each of the sample, like the sample is IID, and then what we do is we find the PDF at each sample point and then we multiply them, right? So to get a loop, first I initialize them both to 1. So one likelihood is for finding with lambda is equal to 2, and the other one is for finding lambda likelihood is equal to 1 for lambda equal to 1. So by putting a loop, I found the likelihood for the samples for different lambdas, and then I'm taking log and then I'm comparing. Can you please explain the t-test again? Okay. So the t-test, see, the t-test is used to compare two distributions. Suppose you have samples from two different distributions. Okay. So the null hypothesis in the case of t-test is whether the means of both the samples is same or not, and the alternate hypothesis is the means are not same. Okay. So the t-test has some specific things. Okay. So what you generally do in t-test is you find the t statistic of a distribution. So the formula for t statistic is given by this for two samples. Okay. So the t statistic given by this y1 bar minus y2 bar by square root of this thing. Here, the y1 bar and y2 bar are the means. S1 square and S2 square are the sample variances. Okay. And N1 and N2 are the length of the sample. So what you do is you find the t statistic, and then based on based on the number of samples and the sample variation, you find the degree of freedom for the t distribution. So and then after finding both of them, what you do is from the t distribution you find the value at based on the significance. Okay, if the significance is alpha, you find the value of value from the t distribution at 1 minus alpha by 2, and then you compare both of them. If the absolute value of t statistic is more than the one that we found, this value is called a critical value. Okay, so if the absolute value of t statistic is more than the critical value, we reject the null hypothesis, otherwise we accept the null hypothesis. That is the t test. What I found is, first I found the sample means and sample variances. Okay, and then I found the degrees of freedom for the t distribution, and then I found the t statistic, and also the critical value, and then I compared them.
Ipsit,
It turns out that the
your voice
absolute value of
is
t statistic
too
is more than
low.
the critical value. So this means the means of the distribution from which both the samples were sampled is not the same. You can see this by plotting them. So if you do the dish plot of both the samples, so this blue curve is the first sample and the orange curve is the second sample. So you can see both have slightly different means and both sort of look like Gaussian. Okay.
So, does anyone have doubts from the theoretical questions, if not from the notebook?
Ramon, you can ask your question.
Yeah, so in the first question of the coding part,
I can't hear you.
you're not able to hear me?
I can hear you. Okay, ask your question. If Ipsit can't hear, I'll repeat it.
Yeah, so my question is basically in the first question of the coding thing, we are
Okay.
we are first asked to find a difference between the log likelihood of two exponential things, and
Yes.
then which of the two is more strongly supported. What is the meaning of this sentence? The second one.
So it means that what is the most likely value of the parameter lambda that fits this sample of distribution?
So between two values, lambda is equal to 1 and lambda is equal to, which one is more likely?
Yeah.
Okay.
Neeraj?
My question was like I just had a doubt. Like just now, Ipsit explained about that we about that like on what basis we we cancel the null hypothesis. So that can you please repeat it? Like,
So it's basically this is called the student's T test. So what we do is based on the sample mean and the sample variance of the two samples that we have, we find a test statistic, and then the test statistic is given by this formula in case of two distributions. Okay, so we find this test statistic, and then we compare this with something called as critical value. So the critical value is found by finding the value from a t distribution. So for that we need some significance level. Okay, so significance level, as I mentioned in the PDF of the assignment, is nothing but by how much error you can tolerate while accepting a hypothesis. Okay, so here I chose a significance level of 0.05. So suppose the significance level is alpha, what you do is you find the value of 1 minus alpha by 2, and then from the t distribution you get the value of the PDF at this point, and we call it as critical value. Okay, so now what we do is we compare the value of the t statistic that we have and then this critical value. If the absolute value of t is more, we reject the null hypothesis with this significance, otherwise we accept.
okay, yeah.
So Abhilash Mishra, you're asking how to visualize an exponential distribution with various value of lambda. So what you do is you just create a some dummy independent variable using line in numpy line space, and then you put a loop, and then you plot each for different values of lambda the distributions using the this plot. So in that way you can visualize the distributions for different values of lambda. Like it's like the way that you plot, like you normally plot any sine function or cosine function or something like that.
Have you guys gone through the PDF for the theoretical questions?
Okay. Just a second. Yeah, you can tell. Hello.
Maybe read out the first question and let's go down.
Down.
Yes, read out the first question and let's pause for question.
Okay.
Their doubts and then go.
You're the first question. The probability density function for an exponential random variable is given by this. Find the mean and variance and find the cumulative distribution. Okay, how do we know which distribution best fits best to our data? Path, can you answer this? Okay.
Yeah, let me see if I can answer it. So first of all, we never know which distribution best fits your data. Okay, the distribution that best fits your data is a distribution which has only impulses at each of the samples that are given, but that will not generalize to new samples. If you divide the samples given into, let's say, two different parts, and you fit a distribution on one part and it still explains the held out part, then it's a good distribution. Okay. So the only way to answer is that, let's say I fix two distributions, then I can tell you which one fits better. I cannot tell you which one fits the best. Or another way to put it is that, let's say I fix the form of the distribution, that the form of the distribution is exponential or Gaussian. So within exponential, I can tell you which one is the best. Within Gaussian, I can tell you which one is the best. Between exponential and Gaussian, I can tell you which one is the best using MLE. But I cannot tell you of all the possible distributions which one is the best. Does that answer your question, Vidya? Uh, Regarding yesterday's pre-quiz,
Equals.
so let's go through it after this. Let's go to the second question. Can you go through the second question?
Game of sun up, sun down. You are given a pair of dice and have to estimate the sum you will obtain before rolling the dice. Your estimate must have exactly one of the three categories: less than 7, equal to 7, greater than 7. Find the probability of each category and the cumulative distribution function of the sum. Using the CDF obtained, find the smallest n. So in a game of n up and down, the probability of n down will be greater than 75. Maybe path. Can you discuss
Okay.
this?
Okay, so what we want to do is we want to estimate the probability that the sum is less than n. So we can find the PMF for the sum, and then we can use it to see which answer gives us a probability of greater than 75%. So we know that there are 36 possible outcomes, and we want a probability of less than n to be greater than 75%. So we should get at least 27 favorable outcomes. So what we can do is we can write down the sum in descending order and see for which value of n we are getting at least 27 outcomes. So the maximum possible sum is 12, and that is only one outcome. So probability of being less than 12 is 35 by 36. And if you see for sum equal to 11, then you have a total of three outcomes where sum is greater than or equal to 11. So that's 6 6 and a 5 6 or a 6 5. So for that, we'll get a probability to be 33 by 36. And like that, if you do it for n equals 10, you see that for n equals 10, it is just above 75%, and for n equals 9, you get it to be around 72%. So the smallest n will be n equals 10. So are there any doubts in this? Okay, so Akhilesh, you want to know what a binomial distribution is with an example. So if you consider like you're tossing a coin n times and you want to find out uh, the total number of heads or total number of tails you're getting. So let's say I define a random variable which is 1 when I get heads and it is 0 when I get tails. So the total number of heads will be the sum of all possible all outcomes, right? All values the random variable takes for each outcome. So the binomial distribution is a sum of IID Bernoulli distributions, IID Bernoulli random variable, which is when the experiment is performed n times. So what we want to do is, let's say the coin is tossed 10 times and we want exactly 5 heads. So what it can be possible when you can choose any 5 of the tosses to take heads, and the rest 5 will take tails. So for for getting 5 heads and 5 tails, the probability will be p power 5 and 1 minus p power 5, and this is possible for any 5 of the 10 outcomes. So what you do is you choose 5 from the 10. So that's why the probability that you get 5 heads will be 10c5, which is the number of ways you can get 5 heads, and the probability of getting 5 heads will be p power 5 into 1 minus p power 5. Does that answer your question? Okay. So if there are no other doubts, we'll move forward with the assignment. Okay. So for the third question, a Poisson random variable has the distribution given here, and there is a small typo. It's p of n, not p of x, but I think that's okay. And we want to find the mean. So the mean is the expected value of the random variable, right? So when you want to find the mean, what you want to do is you want to sum over all possible values the random variable can take, and the sum is a weighted sum of the values, where the weight is the value of the PMF. Right? So it is summation xi p of xi. So here we can write it as a summation. So summation of e power minus lambda lambda power n upon n factorial into n, where because p of n is lambda power n e power minus lambda upon n factorial, and n is the value it takes. So if you sum that up, so yeah, lambda will be greater than 0. It does not have to be greater than 1, but it will be greater than 0. So here the trick is that when you multiply n above and below, so you get lambda power n e power minus lambda upon n minus 1 factorial. Yeah, so the limits will be 0 to infinity, but you can see that the value for 0 won't count. So when you write it as in the n minus 1 factorial form, you can take it to be 1 to infinity for the sum. And like you can use the Taylor expansion of e power x, which is 1 plus x by 1 factorial plus x squared by 2 factorial to find it, and you will get the value to be lambda. Are there doubts in this question? Okay. If it can, you go to the fourth question. Okay, so this is also similar to the dice question. So we have a three-sided die, so it takes values 1, 2, or 3, and it is rolled twice. And again, we are interested in the sum and also the absolute difference of the outcomes. So there are two random variables here. One is the sum of both, and one is mod of the two outcomes you get, mod of the difference of the two outcomes you get. So I think I'll share my screen so it will be better for you guys. I've written it down here. Can you guys see my screen?
Yes.
Okay, so right. So this is the fourth question, and wait a second. I'll just get a cursor. Right. So here we have x, which denotes the sum, and y, which denotes the difference. So x can take values from 2 to 6, right? Because it is a three-sided die. So the outcomes will be, the smallest sum will be 1 for 1 comma 1, which is 2, and the largest sum will be for 3 comma 3, which is 6. So if you want to write the PMF, we remember that the PMF is the probability that both events happen simultaneously. So let's say we want to consider the event that sum is equal to 2 and difference is 0. So that will happen when the outcome is both ones, right? So the probability of that will be 1 over 9 because it is one of the 9 possible outcomes. Similarly, if you consider, the question asks for x equals 4. So if you consider for x equals 4, we have 1 comma 3, 3 comma 1, and 2 comma 2. These are the possible outcomes which give you sum 4. And for these, for 1 comma 3 and 3 comma 1, we have absolute difference 2. So these are two outcomes, and we have the probability 2 by 9. And for 2 comma 2, the absolute difference is 0. So we have one outcome, and that corresponds to probability 1 by 9. So now that we have Pxy, which is the joint distribution, we can find the conditional distribution using this formula. So P of y given x equals x is the probability of their intersection upon the probability that x takes that value. So this is p of y equals y intersection x equals 4 divided by the probability that x is equal to 4. So for y equals 0, we have exactly one outcome, which will give this, and the probability that x equals 4 is 3 by 9, because these are three outcomes out of 9, right? So this division gives us this probability, which is 1 over 3. For y equals 1, there is no such case where the difference is 1 and the sum is 4. So the probability is 0. And for y equals 2, we have two such outcomes, which are 1 comma 3 3 comma 1. So the probability is 2 over 9 divided by 3 1, so it's 2 by 3. Okay, so are there any doubts in this question?
Yeah. In the second part of this question, the which says the conditional distribution probability of y given x equal to 4.
Right.
Uh, like, what is the meaning? I thought, are we trying to find a probability or are we trying to find a distribution? Because in the question it says distribution, so I'm a bit confused.
Okay, right. So yes, you're right. I meant to write the PMF, but I've written distribution here. So this what I've written here is the PMF, and from this you can find the distribution. Does that answer your question?
So we are trying to find the PMF.
Yeah, the PMF, the mass function.
So basically, y can take all the possible values given x equal to 4. We are trying to find the probabilities
Right.
of
Yes,
this.
yes. Are there any other questions? Okay, so we'll move on to the fifth question. And here we are given the joint distribution of two continuous random variables x and y, and we want to find the marginal densities, and we also want to see whether they're independent or not. So the formula for marginal densities is that if you want to find the marginal density for variable x, you integrate out the other random variable, which is y here, and from that you can get, as you can see here, that if you integrate this from 0 to infinity, here x is a constant, right? So you can remove x out of the integral, and this is just integral 0 to infinity e power minus y dy, which is 1. So we get f of x equals x e power minus x, and I forgot to write one thing here. It should be for x greater than 0. And if we want to consider f of y, similarly, you can integrate this, and you get x e power minus x e power minus y dx, because you want to find y. And again, this integration will give you e power, yeah, right. One more thing, so x e power minus x dx, so you can either integrate this by parts, or you can use the fact that this is equal to the gamma function gamma of 2. If you remember, in the lecture we had mentioned the gamma function while describing the gamma distribution, and you can, the gamma function is essentially um, gamma of x is integral 0 to infinity. And if you remember, it has a nice property that gamma of x, so we can use this, and gamma of 1 we have already found it out here, so we can use that. So gamma of 2 is 1 gamma of 1, so it is exactly e power minus y. Again, this is for y greater than 0. And finally, we want to see whether they're independent or not. So recall that for if two random variables are independent, then their joint distribution, the joint density function is the product of individual density functions, or the joint distribution is the product of individual distributions. Right. So we know that the joint distribution given was x e power minus x into e power minus y, and it is equal to this product, right, f of x into f of y. So we can say that they are independent. So are there any doubts? Okay, so I'll move on. The first question for Emily is to find Emily for
Part.
yes,
So they want to, they're asking to explain the independence part again.
for the fifth question.
Yes.
Okay, so when you have a probability, like we have a continuous random variables here, so when you have probability density function of a continuous of a joint density function of continuous random variables, it is fx comma y, right? So if the condition for independence is that if the joint density function can be expressed as a product of the marginal densities. So let me add some subscripts here. Fxy is the joint, the subscript xy indicates that it's the joint density. F underscore x is the marginal for x, and this is the marginal for y, right? So what we have done is, given this, we found fx of x and fy of y, and now we see that it is the product of these two, right? This one and this one. So that is why it satisfies the condition for independence, and we can say that they are independent. Is that okay? Okay, so I'll move on to the MLE question. So what we are given here is that we have n IID Bernoulli random variables, and we want to find the MLE for P. So P is the probability that the Bernoulli random variable takes value 1. And so the steps in finding MLE are that first you find the joint distribution, and then you find the likelihood function. And MLE is the value of the parameter P, which will maximize the likelihood function. So it will maximize the joint PDF at the at the value of samples which you have observed. So let's say you observed random variables are capital X's, and what you observed is these small x's, right? So x1 up to xn is what you observed in the experiment, and now you write it as, if we assume that the parameter is P, then the joint distribution will be this. So we write this using independence. It is a product of all the marginal distributions. And so you can simplify this product as this summation, because they are the exponents, right? So they'll get added. And now this is the likelihood function. And the what we want to do for finding an MLE is, we want to find the value of P which will maximize this likelihood function. So we use a method known as maximizing log likelihood. So what we do is, since log is a one-to-one function, right? So if you plot the graph for log x, so whenever the value, the likelihood is maximum, the log likelihood will be maximum. It is a one-to-one correspondence. So this is why we can maximize log likelihood and say that that value will also maximize the likelihood. So I've written this log likelihood over here. So log likelihood is summation xi log p plus n minus summation xi log 1 minus p. Right? So now what we want to do is, we want to find the value of p which will maximize this function. So we'll differentiate it with respect to p, and what we get is summation xi. So derivative of log p is 1 over p, and derivative of log 1 minus p is minus 1 over 1 minus p. Right? So if you calculate the derivative and equate it to 0, what we get is this expression. And from here we get the value of the MLE for P is summation xi over n. So you can see why this kind of makes sense, right? So if you're tossing a coin and 10 times and you get 4 heads, then the, it is quite close. It is you can intuitively understand why P should be summation of xi over n, because it should correspond to the frequency you are getting, right? So that is just for intuition, and this is what we get as the final result. So MLE for P, given that you observed these samples xi are summation of xi over n. So if I've got 4 heads out of 10, then the MLE for P will be 0.4. Are there any doubts? Okay, I'll move to the next question. So this next question is that we have been given the PDF for a uniform continuous random variable, and we want to find out the MLE for capital N. So we can write the, so first we'll visualize the PDF to get some intuition about it. So this is the PDF for a single random variable. So for values between 0 and capital N, the PDF value is 1 over n, and outside it is 0. So now given this, uh, we will write the joint distribution function of the samples we obtained. So how I've written this is that first, if we are observing samples, let's say x1 to xn, uh, then it means that uh, x1 and xn should all be such, are all distributed like this, right? So if any of these x is greater than capital N, so we are considering candidate n's, right, for the likelihood function. And if there is an n, there is a value of n which is such that one of the observed values is greater than that value, there we know from the PDF that if you integrate it, let's say this is some x1 for a candidate n, if you integrate this area from here, you will get 0, right? So it means that given the value, given a candidate value of capital N, we cannot observe any sample whose value is greater than that. So which is why we write here that if the maximum value observed is greater than capital N, then the likelihood function will be 0. And if it is less than or equal to capital N, then each sample has equal probability of 1 over n, right? Because this is distributed uniformly in this interval. So the joint distribution will just be the product of 1 over n, n times, small n times. So we'll get 1 over n power n, which is the joint distribution. So maybe I write. So now what we want to do is, for each n, this joint distribution function is the likelihood function. And we want to find the value of capital N which maximizes this value, right? So, well, one thing to note here is that differentiation is not always the way to find an MLE, because if you plot the likelihood function for different values of n, what you get is for n greater than equal to the maximum value observed, it will be 1 over n power n. So as n increases, it will decrease to 0. But for n less than this value, what you'll get is 0, because you cannot observe a sample which is greater than capital N, right? So now we know that the maximum point for this will be this one, right? But we cannot get this by differentiation because the derivative here is not 0. So I wanted to give this question to emphasize that the the way we find MLE is not only by differentiating log likelihood, because it will give us the local optima, right? So if the likelihood function was something like this, or okay, since we are plotting the likelihood function, let's say it was something like this, then this will be the global and local maxima. So this is what we want. This is the value of the parameter which will give us the maximum likelihood. But here, since there is no such point because the derivative here is not 0, so we want to find the n which maximizes this, and that will be the smallest possible value of n with likelihood which is not 0, right? So it will be the maximum value observed. So here the MLE for n, given that you've observed these samples, is the maximum value of maximum among these values, right? So if you have say 10, 15, 13, then 15 is the MLE for capital N. So is this clear, or are there any doubts on this? Should I move on?
Yes, that's good.
Okay. So the final question is
Harsh
based
has
on
raised his
this
hand.
testing. So what we've been given here is that
Hello, I
yes.
think
Parth.
Harsh has a question. Go ahead,
Okay.
Harsh.
Actually, I can't see the screen. So can someone read the question to me?
He has raised his hand. Harsh, ask your
Okay.
question.
Yeah, Harsh, ask.
So could you go again, please, with this local optima is not equal to global optima?
Yeah, right. So the concept of MLE is that we want to find a parameter value which maximizes the likelihood, right? So what ideally we should do is we should like check the likelihood value for all values of n and then choose the maximum value. But in most of the cases, like before for the Bernoulli case, what we had is that the likelihood function had a maxima. So something like this, right? This has a maxima, and this is actually the largest value it can take, right?
Mm-hmm.
So this is why differentiation will give us this as the value where the derivative is zero, which is the maximum value.
Yeah.
But in this case, since this function is cut off, right, for n less than the maximum value for x, the, the values are directly zero. So there is no point where the slope is zero, which would correspond to a local maximum or a local minimum, right?
Okay.
So the, the point of this question was that we must realize that the ultimate objective is just to maximize the likelihood function. But in most of the cases, you can find the log likelihood and differentiate it to get it. But the thing we must keep in mind is just maximizing the likelihood.
So do we have to check it by plotting, or how do we get to know? I mean, is there a way to know that?
Actually, this is, you could say, a very special case. I mean, usually what we get is that the likelihood function is across the entire domain. So like you can see here that it is cut off at maximum
Mm-hmm.
x, right?
Mm-hmm. Yeah.
So usually if it is across the entire domain, then you would have a maxima in between.
Okay. Thank you.
Okay. Are there any other questions? Okay, so I'll move on to the third question. The third question is based on hypothesis testing. So what we are given is that there are n IID Gaussian variables with unknown mean and standard deviation 1, and there are two hypotheses. There is a hypothesis about this. So the null hypothesis says that the mean is equal to mu naught, and the alternate hypothesis says that the mean is equal to mu 1. What we want to do is find a test that accepts the null hypothesis with significance alpha. So recall what a test is. The test is like when you observe a sample, the test is a function which will tell you the probability to reject it. So let's say that I've observed a sample x1 to xn, and I want to find out whether I want to reject the null hypothesis or not. So the test will tell me. So the test is a function which will take these values as input, and it will tell me whether h naught should be rejected or accepted. So over here, there's another variable, the significance alpha. So this is a parameter in general for test. What it means is that let's say the null hypothesis was true. So the test should reject the null hypothesis only if the probability, uh, the P, uh, the PDF of the probability of observing that sample is less than alpha. So let's say the null hypothesis was true, and the variables are distributed, all xi's are distributed as normal of mu naught comma 1. So one thing we should note here is that the mean of Gaussians is also a Gaussian. The mean of Gaussians random variables is also a Gaussian with the same mean as the distribution. So let's say if they were distributed as mu naught, the mean will be mu naught, and the standard deviation gets reduced by a factor of root n. Right. So let's say we observe these samples x1 to xn, and we find out that the sample mean, so the summation of small xi, the observed values, is some value mu naught plus z. So given that the distribution for the sample mean is mu naught, has mean mu naught and standard deviation 1 over root n, the plot for the PDF will be something like this, right? Where this is mu naught. And now what we are given is that what we've observed is that the sample mean is mu naught plus z. So let's say this is mu naught plus z. Right. So what we want to do is we want to see whether this claim that the mean is mu naught is true or not. So what alpha tells us is that if the null hypothesis was true, we want to reject it only when the probability of observing this sample mean mu naught plus z is less than or equal to alpha. So probability of, right. So what this means is that this is the value mu naught plus alpha. This is the value mu naught plus z, and this area should be like this measures how extreme this is, right? So how far this is from the expected value of mu naught. So the hypothesis will tell you when to reject it, right? So what we want to do is we want to find a test which will tell you which will tell you when to reject it, and such that the probability, if the null hypothesis was true, it will reject it only if the probability of observing that sample was less than alpha. So what, for an intuitive understanding, what we can see is, let's say the let's say we plot the PDF for both the null hypothesis and the uh, alternate hypothesis, and let's say you observe the sample mean to be somewhere over here. Okay, so by looking at this, you can say that it is more like the PDF for mu1 is much greater than the PDF for mu naught, right? So maybe the null hypothesis is actually false. And what alpha does is it quantifies. So it will tell you till what value we should accept. We should not reject the null hypothesis, and beyond what value we should reject the null hypothesis. So here what we want is we want to find this value mu naught plus z, such that if the value is further away from mu naught, like if it lies somewhere here, the probability of it lying here, this area, is alpha. So what we can devise for the test is that uh, we can compare the value of the sample mean with respect to mu naught, and we can make the test reject it if this area is less than alpha. So is that okay? Are there any doubts?
Harsh?
Yeah, I just want to ask: is alpha same as the confidence interval that we were talking about?
Uh,
Can we assume that? I mean,
It's one minus the confidence interval,
okay,
or one
okay,
minus the confidence, not confidence interval. It's
okay.
one minus the confidence.
So can we take alpha as an error in our data?
Alpha is the probability that it happened by fluke, that it happened because of null hypothesis.
Oh, okay.
so is this fine, or do you see any new doubts in the assignment?
Yeah. Again, we apologize that the assignment release was a little late, so you didn't get a chance to look at all the questions. What we'll do is we'll extend the deadline for the assignment by another day, and hopefully you can go back to this tutorial on YouTube if you still have questions, or ask it on Campus Fire, and will still be will be able to get good experience with the assignment. Thank you. Any other questions? All right.
Pre-quiz
Pre-quiz.
doubts, sir.
Yes.
Okay,
Uh,
so yeah,
who wants to go with the pre-quiz?
I go. So which question do you have a doubt in?
Can you open it? Let's just look at that form.
Okay, Ipshit, can you please open the pre-quiz?
Ipsit, can you open the pre-quiz? Thank you.
Okay, so he's asking the first question. Ipshit, okay, so what is your
First
doubt in the first question?
answer. Okay, see, the question asks what is the probability that one of them is black and then one of them is red. Okay, So I'm not asking about any ordering as such. So what I assume is that, so one of them being black and one of them being red is like 10 into 5 in the numerator, and then by total 15 into 14 in the denominator.
Excuse me, can I pitch in for a second?
Yeah, sure.
So that is how you described number of black balls, the number of ways of choosing a black ball and a red ball, right?
Yes.
10 into 5. What is the number of ways of choosing two black balls? 10 into 9.
Yes.
And the number of choosing the red balls is 5 into 4,
So
right?
10 into 9, if I assume the balls are numbered as such.
I
Otherwise,
mean,
I'll take 10C2.
then you are not going across it. 10C2.
Yeah, if the balls are identical.
Well, if you're taking 10C2, then I guess you will end up with 10 by 21.
Yes.
Yes. So, but the answer given was 5 by 21. So yeah, there's a problem. So that's the problem. Yeah, thanks.
Thanks. You should have mentioned them that the balls were identical.
Yeah.
Any other questions? Yash?
Yeah, I mean, I just wanted to confirm one thing.
Yeah.
Does it matter if the balls are identical or not? The probability won't change. I don't think so. See, if the balls are not, if the balls are numbered, then the number of ways of choosing a black ball and a red ball would be 10 into 5 plus 10 into 5. Which one you choose first? And then the number of ways of choosing the black ball would be 10 into 9 rather than 10C2 and 5 into 4 rather than 5C2. So that would give me the same probability. And if you don't number the balls, then everything gets divided by 2. You should still get 10 by 21 rather than 5 by 21 is what I think.
Yeah. So yeah, it wouldn't matter if they are numbered or not, because we are only, when we are talking about black balls, then it becomes a category that is not numbered.
Yes. Yes.
So
I just wanted to get that clear, because see, if I take it as 10 into 5 and 10 into 5 and the rest of them as 10C2 and 5C2, I think I'll get 10 by 21. But
no,
if I
but
number the ball,
it's not just 10C2 and 5C2, right? It's also 10C1 and yeah, so 10, yeah, so there is also like you can get one black and one red, right?
yes, so that would be 10C1 into 5C1.
Right.
Right. So everything should add up to 15C2.
Everything should add up to 15C2.
Right. But with 5 by 21, it won't. So that was the only thing I was concerned about.
Yeah.
Thank you.
Okay, so there is another question. If it can scroll down.
This one,
Yes.
yeah, it should be 0.9. Yeah, we have changed the keys. So your scores will be modified automatically based on this. You need not worry.
Okay, are there any other questions?
Right.
Okay, so uh, Amit sir, I sort of have one doubt regarding this first question.
Yeah.
So here I mentioned that two balls are drawn at random at a time.
Mm-hmm.
So shouldn't we be taking only, like, shouldn't consider the order of black and red or red and black, right? So, as two balls are being drawn at a time.
Yeah.
So shouldn't the numerator
What
be
is the
10 times?
probability that one of them is black and one of them is red?
Yeah. So given both of them are being drawn at a time.
At a time, right? Okay.
So based on that, I gave, so the numerator will be 10 times 5, and then the denominator will be 15 times 14.
So it's like they are put back. That's not even an issue, right? Because
Yeah,
this is
that's not
just,
even an issue.
yeah. So this is drawing without, it's basically drawing two balls without replacement.
Yes.
It's not with replacement. Yeah. So what's the doubt?
So I'm sort of confused. I think it should be 5 by 21.
What is the
So
probability that one is
black and one is red.
black and one is red? Uh, Yes, I think so too. Let me think about it more carefully. So 15 balls, right? So so you have basically 10 by 15 probability of drawing a black ball. And after
Yes.
that, you need to draw a red ball out of all the other balls. Or otherwise, and then you will add it up with this 5 by 15 probability of first drawing a red ball, and then it has to be a black ball.
So then I'm drawing them at a time, right? Just
Doesn't
taking
matter.
two.
Doesn't matter. It's if you draw at a time or in sequence, it doesn't matter as far as this question is concerned.
Then that's fine.
Because we
Thank
are
you.
not saying first or the second ball. Yeah.
Yeah,
As
thank
long
you.
as it is without replacement, it doesn't matter.
Okay, thank you.
Okay.
So answer is 10 by 21.
Okay. All right. Thanks everyone. Thanks Ipsit. Thanks Parth.
Thank you, sir.
Thank you, sir.